Hey everyone, sorry about the last minute change of plans this morning. I remembered I had a meeting to go to and a Zoom meeting. Runs from 9 to 11 this morning, and so I wouldn't be able to run class, so I made this video for you to finish off the section on compound interest we were talking about on Wednesday, and then I've got a few more videos for you to check out that should get you through section 9.2. I believe those videos were originally filmed for another class, but the content is the same. So check them out, and they should get you through that material. It just, I think I have different section numbers written on there, and maybe I'm referencing some things that don't quite match in terms of the textbook, but the content, the mathematical content is the same, so it's still good stuff, and it will be beneficial to you. So I'll have those available on eLearning this morning as well. I did want to finish off this compound interest conversation that we had on Wednesday. We started out working with the compound interest with n compounds per year, and we had all these compoundings and all these different n values based upon the compoundings, right? Your annual and your monthly and your daily and all that stuff. And we had an example here with $10,000 investment at 5% interest for 2 years, and gave you the, plug that in the formula in the calculator to get all these outputs. And each of these outputs is different depending upon the n value, which was the number of compounds per year. Okay, so where I wanted to continue with that is, if you were to compound so often that you would consider it an infinite number of times per year. You can't actually have that an infinite number of times, but you can kind of figure out what that would be if you could do it. And we call that continuous compounding. It's essentially a compound every moment of every year. And so there's another formula for that, and it's because you can't plug infinity in for the n value in this formula. Infinity is not a number, and so we can't really do that. But we can do something in calculus called taking a limit. Now, this is not something we're going to cover in this class, but it is a technique that allows us to get from this formula to this formula. Okay, it is very interesting, because what you might notice is that the exponent goes from nt to now rt. The n disappears. In fact, there's no n in this new formula. It's a equals p times this number e to the rt. There's no n in there at all. That's because obviously you can't plug in infinity, right? The r and the t both show up, and so does the p and the a. The only thing missing, you don't have that 1 in there. But now we have this new number here. It's a letter e, but it's actually the number e. Okay, so we use the letter e to represent a number. It's called Euler's number, and it was discovered actually in this process of trying to understand large compounding interest. Okay, or compounding interest of large numbers of compounds. And what happens is, and I won't go through all the mathematics here because it does require some calculus and some things that we're not quite prepared to work through. But essentially, if you take the expression here, 1 plus r over n to the nth power, that thing, and you were to plot that or graph that or look at outputs of that for larger and larger values of n being the independent variable, kind of like we would think of an x, this thing has what we call an asymptote. It's a line that the that the expression gets closer and closer to without crossing. We dealt with asymptotes actually on Wednesday when we worked with the exponential functions. When those graphs, like on the decay function, as it comes down and levels off at the x-axis, that x-axis was the horizontal asymptote because the function got closer to that line without crossing it. Well, this thing has an asymptote as well, and its asymptote is this number e. Actually, it's e to the r. Technically, if that r is a 1 there, then you just get e. And so that e, that base of e, is a number. It's an irrational number, kind of like the number pi. And its value, e, is approximately 2.7182 81 and so forth. There's a bunch of decimals there. It is not a repeating decimal. There's no repeating pattern. It doesn't terminate. There's an infinite number of decimals there. So those are just the first few. Okay, so that's the number for E. Again, where this all comes from, all the details there would be better used or described in a calculus course. So for right now, we're going to use that, and our calculators have that E button on it. It is if you have a TI-83 or 84, it is the second feature of the divide button. Okay, you can also have, it also has an E to a power. It's the second feature of this LN button. I don't know if that's coming in very clear there. So there's a couple different places you can find E on the calculator. If I wanted to evaluate for this situation what continuous compound interest would be, that would be where n is essentially approaching infinity. Again, you can't actually attain infinity, but it's what you would get if you could get there. We plug these things into the formula. So A equals 10,000 times E, that's this number, raised to the RT, well, R is 0.05, times the T value, which is 2. Okay, so all that is in the exponent. So then we just type that in. And of course, I would use the second feature of the LN button right there. That would be your E to a power. That way I can just keep that power there right away. So I would type in 10,000 times that E, second LN, raised to the 0.05 times 2. Alright, so that's what I'm looking at. If it's coming in clear. Then you hit enter and it's about $11,051.71. Alright, and so that's the maximum that you can get. The maximum you can get by changing the n value or by increasing the number of compounds per year. Okay. Now it's off. It's actually a decrease by 1 penny here on this. And again, I explained in class on Wednesday that your calculator's giving some error or creating some error in the algorithm that it's using when it calculates things with these larger values. So I wouldn't really worry about a couple pennies here and there on this, on these assignments. If you were working for a bank, you'd want some technology that would be more accurate. But for our purposes, it's good enough. Okay, so anyway, there is an upper limit. There is no way to compound your interest in such a way that would get you more money than this in a given year, or a given 2-year period, I suppose. Okay, so there is an upper limit to this. And that's because this function has an asymptote, but that asymptote is above the function. So the function is coming up to the asymptote, and the asymptote is kind of like the maximum. And that's what you end up approaching here. Okay? So that kind of finishes off our discussion on the continuous compounding interest. And so it's only for that particular case with continuous compounding that you use the formula A equals P times e to the RT. I call it the PERT formula, okay? Kind of like the shampoo, which I obviously don't need anymore. Anyway, so it's the PERT formula, and all other types of compounding interest would use the other formula with the n's in it, okay? I think that pretty much finishes it off. So then I'll let you go ahead and start viewing the videos for the next section on, inverse functions and composite functions. That's what they are. Yep. So we'll see you guys on Monday. Enjoy your weekend.